So hello everyone and welcome back to this next lecture in the DC to DC converter series, and this is where we had left off when we were completing the flyback converter last time. So specifically, as always, we had gone through these particular waveforms, we had analyzed some of them, and we had talked about some of the future strategies possible. So with this, let's come back here. Before we go, as always, one of the important steps is always to back up all our files, right? When I say backup, I mean export all the parameter files. So let's just go and do that, and we can now create a new simulation. So say export parameters. So with this, we have exported all our parameter files. Now let's export our control specifications. So specifically, let me go to the edit control page. So and we are now done. So we have now backed up our simulation. We are now ready to start a new simulation, which will be the forward converter simulation. So as before I start this lecture, a little bit of brief background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I have full-length video courses, online courses on the MOOC website Udemy. So this is the very first course which I have, which is simulating power electronic circuits using Python. And in this course, I talk about the basics of how to use Python, installing Python power electronics, some basics about circuit theory and power electronics, and finally there is a case study of how to simulate a buck converter. If you are interested more on the digital signal processing side, I have another course which is basics of digital signal processing for power engineers, and in this I talk about how you can use Python for signal processing. So there is a little bit of basic background on signal processing, such as Laplace transform and discrete systems. There is some description how you can use Python packages like SciPy and NumPy to design and analyze filters, and there is finally a case study of how you can design, analyze and implement a low pass filter and a notch filter using Python packages such as SciPy and NumPy, right? The latest course which I have is simulation of magnetics for power electronics using Python, and in this course I talk about how you can model magnetic elements such as inductors, transformers using Python. So there is a basic amount of theory such as how to model an inductor, how to model coupled inductors, and how to model transformers. Eventually there is a case study of how to simulate a flyback converter, right? So the link for these videos is provided in the video of this course, so please do check it out if you're interested. So let me come back here. So now that we have backed up our simulation, we can create a new simulation. So let me just go and call this forward converter, and I'll just paste this same thing here. I will change this to 1 microsecond. Actually, this will have to be much lesser. I forgot. It should be 1 e raised to minus 8, because remember we have a transformer, right? So even though we are actually simulating the transformer at 1000 Hertz, we still need something a little lesser, because 1 microsecond is good enough for a 50 Hertz system, right? Now we finally come to the directory of the circuit files. So let's go over and let's create that directory. So let me come first and let me close down all my spreadsheet files, because we will be opening a new set in the new directory. So let me go and create one. Let me call this forward converter. Alright, so now I'm going to take the directory that is the parent folder, I'm going to take this path and paste it here. Right? This is what we always do. Of course, well, actually I'm surprised. Usually we can also put this. Maybe it was an empty directory, that's why it didn't give me the last name itself. So now we have the entire thing, including forward converter. Save the simulation files. If I go, I should see this empty file. So that means the simulator has picked it up. That's good. So let's go back and let's go back to the main page. Now we can add circuit files. So let's start creating some circuit files. So first let's go back here. Go to the flyback converter and we can pick up the voltage source. We can pick up the load because we need this anyway. We can also pick up this filter. Right? Now for the transformer, we can pick up the transformer as always. Right? We will change some of it later. So let me just go. For some reason my mouse is stuck here. That's better. And let me paste it here. So now we have the files. So we will start changing this very soon, right? So let's have a look at it. Let's first add these files. So I'm going to go to the flyback converter, forward converter rather. Add the voltage source. Let's call it DC supply. Add the transformer. Save it. I will add the filter. And finally we will add the secondary load. Right. So basically we're just building up the same simulation again, just to quickly jumpstart ourselves. And we can just process it. Since it's a working simulation, we know the result, but just in case. And of course we need the parameters. The circuits do not have any detectable errors. We are good to go. So now that we are here, let's go and open these files, because we need to edit them for our new simulation. I will then choose the transformer. And finally we will choose the filter. And the last comes the load. So let's just open all of these. Great. So we have all of them now. So let's go back and check what we're going to do with these different files. So first we're going to start with this. Right. So actually let's start with the transformer. Now as already spoken, in a flyback converter, the main concept of a flyback converter is the opposite dot polarity. So if the primary winding has a dot polarity in the upper terminal, the secondary will have a dot polarity in the lower terminal. Right? This is because you want one winding to charge, or rather to energize when the switch is turned on, and at that time you do not want the secondary to be supplying any current. While when the switch is turned off, that is when the secondary supplies current, and that's only possible when we reverse the dot polarities. So if we want to now go back to a forward converter, we are going to take this dot polarity and move it back to the upper terminal. Right? So when the switch is turned on, the primary energizes, the secondary also supplies a current to the load, right? So it's a complete forward direction energy transfer path. Now, when the switch is turned off, if there are only these two windings, nothing can happen, which means the energy in this transformer, rather the energy in the magnetic field of the transformer, has nowhere to go. So, for that, we need a third winding, right? And that's what this is going to be about. We are going to copy this and paste it here, right? This is our third winding. So, let's just open some of this. So, what are we trying to do? This is, we are basically renaming all of them. So, we will rename this as winding 3. And this is also winding 3. And this is also winding 3. Basically, we have to just change all the windings. You could, of course, actually the smarter thing to do would be to just do a search replace. Let me look for winding 1. Let me replace it with winding 3. Find next. Yes, replace it. Where are we? Find next. We can replace this. Replace it. Okay, good. So we have only done a search replace within this area. That's the advantage of selecting this and doing a search replace. I'm pretty sure you can do this also in Microsoft Excel or just about any other spreadsheet software. Alright. So we have now added a third winding to our transformer. What is the purpose of this winding? The purpose of this winding is that we are now, when the switch is turned off and the energy cannot flow through the secondary or the primary because the switch is turned off, secondary because of the dot polarity, right? What that means now is this energy has to go somewhere, right? And the only place that this energy can go is back to the supply, right? So what that means is, the way we are going to have this is, when this energy, when the switch is turned off and this energizes, this should not do anything. This winding should not do anything, right? What that means is that we need a dot polarity such that this will not do anything when the switch is turned on. When the switch is turned off and there is nowhere for this energy to go, that is when this winding must now supply energy back to the supply. So first I'm going to connect this and let's see what that, it will be a little clearer then. So I'm just going to copy this and go over to the source file, voltage source. So here we have the switch, right? Now the switch, actually this would have been, but what I'm going to do is I'm going to bring this here, right? And let me also copy this. This is term 2. So I'm basically copying both winding terminal 1, winding terminal 2. You can copy it anywhere else, but since there is enough space, we can do that here. Right? Now, I'm going to stretch this. Now here, it would have been convenient if we could have added a few more. Okay, let me just, few more cells. This is possible, we can move it here. So what I would do is, I would move this. This would make a change. And I'm going to connect it here, alright? There is still a little bit of a change left, but I will talk about it soon. So I have connected my third winding. Right? Let me just I'll just try to put these together so that we can actually look at them together. So I have zoomed out, right, so that we can just see the entire circuit. And now let's look at what we're doing. We have this switch, right? We have this prime switch which is supplying the first winding, right? This is the same as before. What we are adding is a third winding that is connected before the switch, right? So try to picture this, or maybe draw this on a piece of paper if you're not really sure. But we are creating two parallel paths to our DC supply. One path is to winding 1, the second path is to winding 2, right? Now winding 3, sorry. So this winding 3, the job of this winding 3 is to dissipate the energy in the magnetic field back to the DC supply when the switch is turned off, right? This should conduct only when the switch is turned off. So we should not have a clear path like this. We have to put a diode here. So I'm going to call this diode. Let's call this freewheel. Okay, probably not the best answer, but the best name, but anyway. So diode freewheel. So the job of diode freewheel is to block any energy going to this winding during normal circumstances, and it has to conduct when the switch is turned off. Then this induced EMF in this winding must supply energy back to this supply, right? The result is now the energy in the magnetic field is never ever broken, right? It will flow either in the forward wire. When the switch is turned on, it will flow in the forward direction through winding 1 and winding 2 all the way to the load, and when the switch is turned off, it will freewheel through winding 3 and the diode back to the supply, right? So we have achieved a forward transfer, and at the same time we are achieving a dissipation of the magnetic energy through the freewheel diode, right? So with this, I'm going to stop this lecture, and in the next lecture we will continue on how we can edit the parameters of this, as well as make changes to the other part of the circuit, and probably also describe this in a little more detail, right? So if you have any doubts, please do post either in the comments, or email me, or message me on social media, whichever is your preference. Otherwise, I will see you next week, where we will continue with this. Thank you so much for listening, and goodbye for now.